In this video, we are going to enhance our knowledge in one of the most interesting and important topic of coordination compound, the electronic spectra and Orgel diagram. Electronic transitions, spectra and color of the transition metal complexes can be analyzed a little bit quantitative manner in terms of Orgel diagram. The name after its inventor, Leslie Orgel, a British chemist. He published his work on Orgel diagram in the Journal of Chemical Physics in the year 1955. Okay, let's start our topic. As we know, being students of chemistry, transition metal complexes are most colorful species around us. Now let us try to find the origin of color of these compounds. For this purpose, we have to understand electronic transitions and its corresponding spectra. For transition metal complexes having d orbitals, their dd transitions are observed, which are generally Laporte forbidden, as we know. Let us see how this spectra arises. Here we consider 5 d orbitals splitted in octahedral field, having one electron in ground state, that is T2G level. When energy of particular wavelength fall on the electron, it absorbs the certain amount of energy and excited to upper energy level, that is Eg. For many electron system, actually electrons in particular orbitals possesses electron-electron repulsion, giving rise to different energy states are called terms. Ligand field and crystal field also taking part in these repulsive interactions, producing more complicated energy states or terms. And among them, these type of electronic transitions are taking place now. Again, the wavelength lambda associated with this energy among two states of electronic transition are most important for the development of peak or spectra, as shown in the slide. If the wavelength belongs to the visible region, we know from 400 nanometer to 800 nanometer is a visible region range for human eye. Then human eye can sense the color. Otherwise, in UV or IR regions, the spectra will be invisible and can be analyzed instrumentally. That means in terms of spectrophotometer. Of course, when a photon of visible light is absorbed during electronic transition, the color which we observed for this compound is nothing but complementary color. We shall focus on the electronic transitions in between different energy level and its corresponding spectra. We have to follow the steps below. At first, for free metal ion, that is metal ion having d electrons in 5 degenerated d orbitals, there occur spin orbit coupling, which is known as LS coupling. Now, due to this coupling, different terms or energy states including microstates arises for free metal ions. Again, for metal complexes, which is generated due to the interaction between metal d orbital electrons and ligand field, such as octahedral field or tetrahedral field, etc., where repulsion between metal d electrons and ligand p electrons are taking place. Due to this repulsive interaction in ligand field or in crystal field, further splitting of d orbitals are observed, which are called crystal field splitting term. For this interaction or splitting, again new energy states arises due to ligand field or crystal field. Some new energy states arise due to ligand field or crystal field interaction, and electronic transitions taking place among these newly arises energy states. These transitions are responsible for the spectra of metal complexes. How the term and symbol can be obtained for a particular electronic system. RS coupling is the suitable phenomenon to finding the term the energy state. As we know, capital L used to explain the total orbital angular momentum quantum number of electrons, and capital S is nothing but the total spin angular momentum quantum number of electrons. Such LS coupling scheme is shown in the figure where orbital angular momentum, which is shown as blue color, and spin angular momentum, which is nothing but red color, are coupled with each other and form resultant total angular momentum J as violet color. This is nothing but the spin orbit coupling scheme. In spin orbit coupling scheme, electrostatic interaction between electrons are generally dominated, and the magnetic interactions between electrons due to intrinsic magnetic moments created by the orbital angular motions are of small perturbations. Interestingly, this spin orbit coupling scheme, which is called LS coupling scheme, is successfully applicable for lighter atoms having atomic number up to 30. That is nothing but first transition metal series. But for heavier atoms, another coupling scheme called JJ coupling is applied. Since their atomic weight is higher, so there occur very high spin orbit coupling, and JJ coupling scheme is applied. For LS coupling, ground state term and excited state terms, including microstate, can be determined for one or many electronic system. How to determine RS term symbol? We know already that how to find term symbol of a particular electronic system using Russell-Saunders coupling scheme. To find the particular orbital at first whose term symbol has to be determined, like metal d electrons, suppose d1 or d2 or d5 or d9, etc. Then we have to calculate the total orbital angular momentum, that is capital L, which is nothing but the vectorial summation of individual angular momentum of the electron of that particular orbital, and it can be achieved from summation of ml values of that particular orbital. Then we have to find the total spin angular momentum capital S, which can be achieved by combining vectorial individual spin angular momentums of electron in that particular orbital. From this capital S value, we can find the spin multiplicity, which is nothing but 2s plus 1, and from this spin multiplicity value as well as that L value, we can construct our term of that particular electronic configuration as 2s plus 1 L. Now we can find J value, which is nothing but the total resultant angular momentum value combining capital N, L and capital S, having formula J is equal to mod L plus minus S. The J has value from L plus S to L minus S. Here a pictorial diagram is shown for spin orbit coupling as well as LL coupling and SS coupling, and finally LS coupling is shown. From this spin orbit coupling, we can find the term symbol of any electronic configuration using the notation 2s plus 1 Lj. Now from the notation 2s plus 1 Lj, we can determine the different term using the values of L as shown in the table below. For the value of L such as 0, the symbol must be capital S. For 1, it must be capital P. For L is equal to 2, it must be capital D. For L is equal to 3, it is capital F. For L is equal to 4, it is capital G. For 5, it is capital H. For 6, it is capital I. For 7, it is capital K. For 8, it is capital L. And for 9, it is capital M. Interestingly, the nomenclature of S, P, D, F, all capitals, is derived from the characteristics of spectroscopic line corresponds to small s, p, d, f orbital, and which is denoted as sharp, principal, diffused and fundamental. Again, the rest being named in the alphabetical order from G onwards, except that J is omitted. Since J is used as total resultant angular momentum quantum number in this term symbol. Finally, combining L and S, that means 2s plus 1 multiplied by 12 plus 1, we can find the term of any electronic system. Likewise, level and state of any electronic system can be explained as follows. Again, another interesting feature that the wave functions for capital SPDF term have the same symmetry as the wave function for the corresponding sets of SPDF orbitals. Hence, a D term is split in an octaedral field exactly same manner as a sets of 5d orbitals are splitted in octaedral field, as well as for F term is split as per the F orbital and so on. Since we like to learn the electronic transitions and nature of spectra for transition metal compounds, then we need at first try to find the free metal DN ion term using RS coupling scheme. Let us consider D1 configuration as shown here in the right side, then find capital L value, which is nothing but 2 here, indicates ground state as capital D and capital S as half. Hence 2s plus 1, that is spin multiplicity is nothing but 2. But here we are interested for quantitative analysis of spectra of D1 system, then we must consider microstate of D1 electrons. Microstate, which is denoted by capital N, can be determined using the formula given here, which is nothing but factorial N divided by factorial E into factorial N minus E, where E is nothing but the number of electron concerned and small n is nothing but the number of possible orbital position. So here in the case D1 configuration, the microstate is nothing but 10. Means the single d electron can be arranged in 5d orbitals in 10 ways, considering the degeneracy of the orbitals as shown in the figure in the right side here. Hence, using the selection rule and Pauli exclusion as well as Hund's rule, from this D1 arrangement only one term is possible, that is nothing but 2D. So for D1 system, the free ion term is 2D. System such as D2 metal ion, where 2 electrons are occupied in 5d orbitals. Normally, the ground state term is 3f as previously done, but considering the microstate as previous slide, there are 45 possible microstate for D2 arrangement. And for orbital angular quantum number capital L value found from small l coupling have values shown in the table that are plus 4 to minus 4, which generate the term G, plus 3 to minus 3, which generate term F, plus 2 to minus 2, generate term D, plus 1 to minus 1, generate term P, and for 0, generate term S. Next, we have to find the spin coupling. From spin coupling, the S value are plus 1, 0, and minus 1 as shown here, and corresponding to S plus 1, that is spin multiplicity values, are as shown here for different S values. Next step is LS coupling, considering all microstates and selection rule as shown in the figure in the right hand side, where 45 possible arrangement of 2 electrons or states are possible. These 45 microstates are covering the 5 terms as we find earlier, that is nothing but 3f contain 21 states, 3p contain 9 states, 1g contain 9 states, 1d contain 5 states, and 1s contain 1 state. The energy ordering of their terms are as shown here, where 3f is lowest in energy and 1s is highest in energy. But from spectroscopy, the actual order is 3f is less than 1d is less than 3p is less than 1g is less than 1s. Among these terms, as per Ohm's rule, the 3f term have lowest energy and hence ground state. Interestingly, for Orgel diagram, we have to consider 3p term also for precise electronic transition. In this slide, different 3D transition metal ion and their various parameters regarding spin-orbit coupling such as capital L, capital S, spin multiplicity and ground state term symbols are represented as tabular form. In this table, like D1 configuration, for example titanium plus 3 having capital L value 2 and capital S value half having ground state term symbol 2D 3 by 2, as well as for D2 configuration, for example vanadium plus 3 having capital L value 3 and capital S value 1 and the ground state term symbol nothing but 3f2, and so on for other system. Before we reach the term of free ion, I would like to explain another interesting fact, that is nothing but electron hole formalism. D10-n configuration have same behavior as for Dn configuration, except the energy or the term order or sign of energy. Here electrons in Dn configuration are compared to the hole or sometimes called positrons in D10-n configuration. Interestingly, their splitting pattern or energy order are just inverse. Here we consider D1 system in an octahedral environment where an electron is in T2g orbital in the ground state. After absorbing energy, the electron excited to the upper energy level, that is Eg level. Again, comparing this transition with D9 system, which is nothing but D10-1 arrangement. Here in ground state T2g6 Eg3 configuration, where a vacant space called a hole is present in the Eg level. During electronic transition, after absorbing energy from T2g6 to Eg3 level, we can say the hole is migrated from Eg to T2g level, and hence it can be compared with the situation with D1 arrangement. One or two interesting feature of hole formalism, that octahedral Dn configuration and tetrahedral D10-n configuration give rise to similar type of splitting. Again, the free ion terms will be split into the same spectroscopic components of terms in presence of crystal field. For example, D1, D9 and D4, D6 configuration will be split into Eg and T2g in octahedral as well as E and T2 in tetrahedral field, and this type of splitting is shown here for D9 spectroscopic term. So from hole formalism principle or hole formalism phenomenon, we find that some couple of configuration which show this type of behavior, like D1 and D9 system, D2 and D8 system, D3 and D7 system, D4 and D5, D6 system, as well as D5 and D10 system. In this slide, I have shown the possible terms of different DN system in tabular form, considering Russell's undercoupling as well as ground state and microstate, different selection rules, Pauli exclusion principle and Ohm's rule. Again, according to hole formalism phenomenon, D1 and D9 configuration have 2D term. For D2 and D8 configuration have 3F, 3P, 1G, 1D and 1S terms. For D3 and D7 configuration have 4F, 4P, 2H, 2G, 2F, 2D, 2 and 2P terms, and so on. For D10 system only 1S term. To construct Orgel diagram for electronic transition, we need generally the ground state term as well as few excited state term. For this purpose, we need Hund's rule. Terms with highest spin multiplicity, that means 2s plus 1 value, has lowest energy. That means that term is nothing but ground state term. So here the highlighted terms are the ground state term. But if when same multiplicity arises for two terms, so we have to consider the highest value of capital L, which possesses the lower energy. That is, for 3f and 3p terms for D2 and D8 system, or 4f or 4p terms for D3 and D7 system, here both these terms possesses same multiplicity, but the L value in the case of f is greater than p. So f term must be the ground state term. Again, in the case of Orgel diagram, not only ground state, in a few cases some excited state are also required. As for example, for D2 and D8 system, not only 3f but also 3p term, as well as for D3 and D7 system, here also 4p and 4f terms are required to construct Orgel diagram. In this slide, we will see the type of ligand fields which interact with the free metal ion term. As we know from our previous concept of coordination chemistry, there are two types of ligand fields or ligands which are classified as weak field ligands and strong field ligands. In the case of weak field ligands, their splitting parameter are very smaller in comparison to their interelectronic repulsion in a particular orbital, and its corresponding pictorial diagram is shown below. And in the case of strong field ligand, the crystal field parameter for these ligands are very large with comparison to interelectronic repulsion of electron in particular orbital. It would more appropriate to consider the crystal field splitting first, and then necessary adjustments are made for interelectron repulsion. Here also a pictorial diagram for strong field case is shown. So we get high spin case in the case of weak field ligand and low spin case in the case of strong field ligand. Interestingly, in the case of Orgel diagram, generally weak field case are considered. How the term, that means free metal DN ion term, are affected in presence of ligand field. As per the previous slide, we generally consider the weak field case for the construction of Orgel diagram. Here, the free ion terms of different DN system are further splitted into different new components in presence of ligand field or crystal field. And these terms are coming from the application of group theory. I will discuss it in another video. So let us see how the free ion terms of different DN system are further splitted into different crystal field terms in tabular form. Here, capital S term for free ion are splitted into A1 crystal field term. For P, it is splitted into T1 crystal field term. For D, it is splitted into E and T2 crystal field terms. For F, it will splitted into A2, T1 and T2 crystal field terms. For G, it will splitted into A1, E, T1 and T2 crystal field terms. And the suffix G arises in the case of centrosymmetric molecules as for octadrill molecules. Some interesting feature of these crystal field terms. Number one, spin multiplicity is not hampered due to ligand field. That means the 2s plus 1 value is same for both free metal ion term as well as the term arises due to presence of crystal field. Number 2, for centrosymmetric compounds, all split terms are labeled as G. G means Girardet. The use of G or U are not applicable in the case of non-centrosymmetric molecules. Again, S and P terms are not split in octahedral field. Now, the sum of degeneracy of the individual component in the octahedral field is equal to that of the original term. That means the overall degeneracy must be conserved. And at last, the inverse splitting relationship also observed for the octahedral DN configuration and tetrahedral DN configurations. What we have done till now, we have selected some transition metal DN ions and find atomic terms for those metal ions such as capital S, capital P, capital D, capital F, capital G, etc., applying Russell-Sanders coupling and interelectronic interaction considering microstates. Then we imposed ligand field interaction, especially weak field situation on the free metal ions, rather free metal ionic terms, and try to get some crystal field terms or components as A1, A2, T1, T2, E, etc. for tetrahedral cases or non-centrosymmetric cases, and A1G, A2G, T1G, T2G, EG for centrosymmetric octahedral cases. Now let us see how these free ion atomic terms as well as crystal field terms are used to construct Orgel diagram. Correlation diagram of D2 free metal terms and the crystal field terms arises from it in presence of weak field as well as strong field ligand environment are shown. In the left side, free metal ion terms for D2 configuration and its components of terms in weak field and strong field cases are shown. Also, how the 45 microstates are distributed in the corresponding terms are shown here. The number of microstates will be same in weak field as well as strong field environment, but their energy ordering are different. Once again, from the splitting pattern for D2 metal ion, we need only 3F and 3P terms and their components to draw the Orgel diagram. Now we are ready to draw Orgel diagram for electronic transition of different DN metal complexes. This is the Orgel diagram of D1, D9 and D4, D6 metal complexes in weak field environment. They may have tetrahedral or octahedral geometry. Here the diagram is shown where these metal ions D1, D6 and D4, D9 including their geometry are represented in both the sides. This diagram is a energy correlation diagram drawn energy of the system versus delta, that means crystal field splitting parameter, where delta value increases both the side left as well as right in same manner irrespective of sign. Here the whole formalism principle, as we know from earlier slide, is strictly maintained as represented in the diagram. The DD transitions for D1, D4 octahedral system and D6, D9 tetrahedral systems are represented in terms of Orgel diagram. Here, for these systems, we have to draw the right hand side portion of the Orgel energy correlation diagram as shown previously, as well as here it is shown again in the right side, and the corresponding transition is 2T2G to 2EGD for octahedral cases and 2T2D to 2ED for tetrahedral cases as designated here. Now we can find the wavelength lambda as in the equation inverse of wave number or energy involved in the transition, and from the wavelength we can identify the position of absorption or spectra as well as the color of the complexes. Here an example of electronic spectra of titanium hexaquark 3+, a D1 system is shown, which is found experimentally using spectrophotometer. Again, delta O value or delta T value can be calculated from the splitting of D2 term as shown in the slide. Here the electronic transitions for D1, D6 octahedral and D4, D9 tetrahedral systems are shown in terms of Orgel diagram. For this type of DN systems, we have to follow an important trick to depict the energy correlation diagram from the standard Orgel diagram. As shown here, we only draw the left hand side part from the standard Orgel diagram but inverted or flipped horizontally. Of course, there may have other conventions and other parts are same as previous slide. The electronic transitions from E to T2 for tetrahedral and EG to T2G for octahedral and its corresponding energy involved, also its related wavelength, absorption region, peak positions, color, etc. can be achieved. Here an absorption spectra of copper hexaquark 2+, a D9 complex is shown, which represented the EG to T2G transition. We also can find the 10dq or del value from the splitted 2D term. In this slide, Orgel diagram of D2, D3, D7 and D8 tetrahedral and octahedral system in weak field environment is shown in one frame both left and right side. In this diagram, as I told earlier, for these DN configuration, capital F and capital P, both these free ion terms and their components as crystal field terms are considered. The spin multiplicity is 3 as 3F, 3P for D2 and D8 system and 4 as 4P, 4F for D3 and D7 system. Their corresponding components also bear same spin multiplicity. How we can represent different electronic transitions for D2, D7 system in octahedral field and D3, D8 system in tetrahedral field in terms of Orgel diagram are shown here, where we choose the left hand side part of the standard Orgel diagram. For this electronic system, 3 possible transitions are allowed. Number 1, T1GF to T2GF. Number 2, T1GF to T1GP. And number 3, T1GF to A2GF. Here, T1GF be the ground state. And from the energy involved in these transitions, we can calculate the wavelength lambda and the position of absorption in experimental spectra. Again, we can calculate the 10dq value from the splitting of F term as shown here. For these configurations, the energy gap between T2 to A2 provide 10dq value. From these data, we can interpret the spectra and the color of their complexes. So, the D2-D7 configuration in octahedral field and D3-D8 configuration in tetrahedral field are represented in left hand side energy correlation diagram of standard Orgel diagram, but it is horizontally flipped or inverted as earlier. Hence, now A2F state becomes ground state, and the three transitions are A2F to T2F, A2F to T1F, and A2F to T1P. We must use G for octahedral involvement. From these energy involved in these transitions, we can find the corresponding wavelengths and absorption position from experimental spectra, and also interpret the color of their complex. 10dq value may be calculated considering T2 to A2 splitting of F term. For my current lecture, here we have learned the electronic transitions of DN systems in different ligand environment through Orgel diagram. Here, due to constraint of time and guideline of BSc syllabus, I couldn't explain microstate and generation of crystal field terms from group theoretical interpretation elaborately. If it is my request you all to memorize the terms for the construction of Orgel diagram. Those who are interested can visit my next video on Orgel diagram part 2, where I will discuss the construction of Orgel diagram of different transition metal complexes and interpret their transitions, spectra and color in detail. Thank you for your patience.